Great. Good morning, everyone. My name is Minguk. I am from Texas A&M University. I'm a second-year PhD student, and today I'm going to present about our research on identifying the potential of human-inspired inverse reinforcement learning approach for lunar surface construction. So I'd like to begin by introducing our research background first. So unlike a typical construction site, the lunar surface requires robot to operate in its unique conditions, like situations. So it involves its inherent environmental features, severe resource constraints, or limited human accessibility. On top of that, the robots may encounter with complex and dynamic operational contexts, such as encountering with unidentified object in the lunar surface construction area, which may come from another country because the lunar surface is gray area for now. These challenges necessitate the more higher autonomy, or level of autonomy. However, the existing commercial construct robots, they are not designed for this level of autonomy. They typically come from manufacturing paradigm, operating in controlled environmental settings, and performing repetitive tasks with human intervention. These are actually effective in structured and supervised settings. However, when you shift to the extreme workplaces, it may suffer from its methodological its limitations in such conditions. Meanwhile, in the research community, there has been increasing interest in learning-based approach, especially imitation learning. So imitation learning aims for training an agent by using expertise demonstration data. So existing studies, they have shown its promising result. However, the conventional imitation learning approaches, such as behavior cloning or adversarial imitation learning, such as GAIL, they suffer from their methodological limitation, which is that, firstly, they merely just mimic human actions, not their decision-making strategies. And secondly, they are heavily dependent on deep neural networks, which require high data dependency and high computational burdens. So how to mitigate these challenges? I'd like to focus on three main approaches. The first one is we need to develop a new imitation learning approach that reduces data dependency and enables lightweight computation. And secondly, the new approach must be capable of imitating human decision-making, not just their actions. And on top of that, we found out that existing studies, they use generic simulators such as Unity or PyBullet. However, they often overlook or underestimate the importance of fidelity improvement step. So if the fidelity is not properly addressed in simulation step before the training, the difference between the simulation and the real world makes the agent's performance really goes bad. In this case, based on these approaches, I'd like our research motivated by just simple human theory, which is that humans decompose a complex main task into several meaningful subtasks and then integrate it into a single coherent decision. So to implement this, our research adopts inverse reinforcement learning approach, which estimates experts' decision signals from their demonstration data. So this slide shows the proposed frameworks overview. So to explain this, let's assume that we have an excavator robot, and we want the excavator robot to reach the designated dump area with a shorter path and while avoiding moving object or fixed object. Then the first step will be task modularization. So dividing a main construction task into several subtasks, and the tasks will have its own behavioral goals and associated objects. And then state and action space of each subtask will be defined accordingly. Then the next step is fidelity improvement step, which includes physical fidelity, such as applying high resolution lunar terrain data, and functional fidelity, which, for example, like refining physical interaction in simulation to be more realistic and ensuring sensory integrity. And then the next step is parameter estimation, where the agent estimate the parameters of the agent or parameters of the human by using the sampling method. So once the parameters, so in this case, the parameters are reward values and the discount factors anyway. So once everything is done, the estimated parameters are applied into the Excavator agent, and then the agent will interact with the environment. So the interaction is actually the iterative process until the given task is done. So the first step will be data perception, where the agent perceives data from each surroundings and itself. And then the agent simulate all the candidate action by using a virtual bucket replica in the simulation to calculate the spatial distance and temporal distance of bucket, like from the distance between the bucket and each key object, such as rubber, rock, terrain, and dump area. And then the agent, by using those distances, the agent can compute Q value for each subtask, which can be aggregated into a single global Q value. So it means that all the actions are, so all the candidate actions have its own expected value. So by using those values, we can select actions probabilistically. And then once everything is done, the bucket trajectory can be visualized like the figure on the right. So up to this point, I've explained about how the proposed framework works, and then now I'd like to explain about how did we evaluate the proposed framework. So evaluate this, we selected one baseline model, which is behavior cloning, because behavior cloning is a prevailing and representative approach in construct robotics, especially when used the imitation learning. And we selected two key criteria. The first one is similarity, which reflects that whether the agent will follows the human strategies, and the robustness, which reflects that whether which reflects that how well the agent perform well in dynamic and complex environment. So this slide shows the overview of the experimental procedure. The first one, we generated 70 scenarios by using random environmental variables such as object location and moving roll path and velocity and rock direction and size. And then by using the 40 out of 70 scenarios, we collected human demonstration data. And then we trained the behavior cloning agent or estimate the parameter for the proposed frameworks agent. After that, we evaluate all the agents by using the list of 30 scenarios. So this slide shows the results of the experiment. As you can see, first of all, for the similarity, the agent achieved 78% consistency in route selection with the human, which means that the proposed framework can capture the expert strategies effectively. And then robustness, the agent modeled by the proposed framework achieved 73% task success rate, which is 46% higher than the agent baseline model. So it also means that the agent can perform well in the extreme work settings. So I'd like to finish my presentation in this slide. So we proposed a modular inverse reinforcement learning approach for the extreme work settings, and then it achieved 73% task success rate, outperforming the baseline model. So theoretically, it mitigates fundamental constraints like limited data and computational research, which is the limitation of the extreme work settings, and then it models high-level expert decision strategies and formalizes the simulator fidelity improvement for the generic simulators. And then practically, it enables autonomous system to emulate the expert decision making, and we expect that it improves development accessibility for the generic simulators and facilitates the modular reusability and scalability for the future construction robotics. So that concludes my presentation, and thank you for your attention. And